Welcome and thank you for being here today. My name is Tashiana Osborne and I'm a PhD candidate at Scripps Institution of Oceanography of the University of California, San Diego. I work within the Center for Western Weather and Water Extremes, and I study atmospheric rivers or low-level rivers in the sky. During this summer school, I'll be sharing about extreme rain and snow events that affect the Western US and other regions of the world. I'll also be sharing a bit more about my personal journey and some of the growth that I've experienced through extremes. I'd like to start out by sharing this quote from Dr. Cornel West, who I had the pleasure of meeting back in 2012. I try to use this to drive the work that I do. He said, "We've forgotten that a rich life consists fundamentally of serving others, trying to leave the world a little better than you found it. We need the courage to question the powers that be, the courage to be impatient with evil and patient with people, the courage to fight for social justice. In many instances, we will be stepping out on nothing and just hoping to land on something. But that's the struggle. To live is to wrestle with despair, yet never allow despair to have the last word." And when I read this and when I think more about it, it prompts me to ask myself, and maybe it'll prompt you as well to ask, what can I do in service of others? What can I do in service of my community and others? Of course, there's no one-size-fits-all answer, but this is something that is worth thinking about and continuing to think about as the world goes on. Now I'll get a little bit more into what I study. So the first rule of meteorology that I learned is that the atmosphere, maybe like our lives, is in a state of constant chaos. What this means is that any change in initial conditions, or even any small change that occurs over time afterwards, can dramatically alter the weather conditions that we see or the result that we end up with. And so what this means is the difference between a thunderstorm forming and creating a lot of rain versus no storm at all. We have some ingredients that we need to create storms that involves atmospheric instability, lift, and moisture in the atmosphere. My work generally falls somewhere within the water cycle, between meteorology, hydrology, and oceanography. The part that I'm really interested in and have been for a while is the precipitation piece, especially when it's extreme rain and snowstorms. As we've learned from past and current studies, the mean global surface temperature has been increasing since the Industrial Revolution and at a more dramatic rate in more recent times. So the plot I'm showing here on the right is a time series with the year on the x-axis, the difference from the 20th century mean temperature in degrees Celsius on the y-axis on the left-hand side, and the right-hand y-axis is showing the CO2 concentration in parts per million. The 20th century mean is approximately 13.9 degrees Celsius or 57 degrees Fahrenheit. We see the temperature deviation from this mean move from negative values in blue from 1880 to 1940 to positive values in red. In fact, in 2019, global mean near surface temperatures were nearly 1 degree warmer than the 20th century mean. Following along with this trend is the CO2 concentration line shown here in gray. Climate change, we know, is affecting the water cycle, air temperature, weather patterns, the intensity and frequency of storms and droughts, mountain snowpack, sea levels, and much more. For example, increasing air temperatures in the low atmosphere, which is the troposphere, can contribute to increased evaporation rates. And as a result, the amount of moisture or atmospheric water vapor circulating through the troposphere would increase, which would mean an increased frequency of instability that can lead to intense storms. In addition, due to warmer temperatures, more precipitation can fall as rain rather than as snow, and this would mean we'd continue to see changes in timing and overall decreases in our mountain snowpack, which is critical to water supply. The increasing CO2 concentration that we see stems largely from human-created factories, processes, and machines. Animals, including humans, and plants play key roles in the carbon cycle and also the water cycle. But we also know that animals and plants can only thrive in certain accustomed temperature ranges and climates. Within the carbon cycle, plants and forests take in carbon dioxide to complete photosynthesis. The ocean uptakes and retains large amounts of CO2. Meanwhile, plants and animals actually release CO2 through respiration. CO2 is also returned to the air in decomposition stages post-mortem. Predictions of a warmed world may intensify when we account for delayed responses of ice albedo, cloud, and other known feedbacks, and also the large amounts of CO2 and other greenhouse gases currently stored in the oceans, plants, soil, and permafrost. So there are currently 7.8 billion people living on Earth, and we have reached a CO2 concentration above 413 parts per million. Carbon dioxide concentrations and warming are projected to continue increasing unless we, as humans, take swift, significant, and effective actions to move away from a business as usual or an even worse case scenario. Now, some of the questions that I think about in my research. How can research help California communities, forecasters, water managers prepare for and protect during extreme weather and water events? And broadly, what can we learn from previous extreme precipitation events to help moving forward and planning for future storms? And then more specifically, my research question, which is how can we define, detect, and describe rapid and significant, or what I'm considering extreme, changes in the amount of rain versus the amount of snow experienced during California storms? California has wild swings between drought periods and wetter periods that are brought on by atmospheric rivers. I'm showing the coefficient of variation for annual precipitation from 1950 to 2008. The green, blue, and black are showing higher variability from one year to the next, which we can see over the California region. Precipitation varies greatly from year to year, whereas on the eastern side of the US, the total precipitation varies only slightly from one year to the next. So a lot of these storms that bring us the majority of our rain and snow in California are called atmospheric rivers. And I'll talk a little bit more about those in the next few slides. Atmospheric rivers provide California with up to 50% of our water supply. They're known to be drought busters, but they can also result in challenging and destructive extreme storms. So what are atmospheric rivers? They are plumes of high water vapor in the low atmosphere that stem from near tropical regions. Typically, they actually impact more than 40% of the world's coastlines. They can contribute to 40 to 75% of extreme wind and precipitation events. On the other hand, they can also be beneficial, as I said, for the Western US, providing up to 50% of our annual water supply. This moving image here is showing the water vapor in the atmosphere, and some of these plumes or ribbons in the sky that you're seeing are actually atmospheric rivers that are reaching land. Atmospheric rivers, they form over the ocean, but they do end up interacting with land if they can travel far enough to make it there. And so once they do reach land, they interact with the topography in unique ways. So along California's coast, the moisture is actually forced upwards where it can cool and condense to create these storm events. And that's what we call orographic precipitation enhancement, where we see an enhancement of precipitation on the windward or west side slopes of the mountain ranges, including the coast ranges near the coast, and then further inland as the storms penetrate inland to the Sierra Nevada. Atmospheric rivers that reach the western US are typically around 850 kilometers wide, greater than 1,500 kilometers long, and about 3 kilometers thick. And they actually exist about 1 kilometer up from the Earth's surface. Here's a satellite view of an atmospheric river, and you can see that it's extending from near tropical regions where it formed through unique ocean-atmosphere interactions over to the western US where it has traveled. We're seeing the clouds there, the cloud formation. Most of these storms are associated with a low pressure system, a mid-latitude cyclone, or extratropical cyclone. Atmospheric rivers occur during California's cool season, which is between October and April. We actually go out across California, mostly northern regions of California, and launch weather balloons during the storms every couple of hours. Attached to these weather balloons are what we call radiosondes, which measure different variables within the atmosphere as they ascend. And then we also have level loggers, which can measure water under the ground. We have ways to measure stream flow, and then also some of the variables that are important to us underground, like soil moisture and temperature. So we can think about how that changes during and after an atmospheric river. There's also a really neat part of this data collection piece that I've been really excited to learn about, which is the Atmospheric River Reconnaissance mission that is part of the Center for Western Weather and Water Extremes in partnership with the US Air Force and the NOAA Hurricane Hunters. So these aircraft, the Hurricane Hunters that some of you might have seen flying through hurricanes and releasing different instruments during the hurricane season, are actually available for our use during part of the atmospheric river season, since it doesn't overlap with the hurricane season. The two aircraft that are generally flown are the NOAA G4 and the Air Force C-130 aircraft. These aircraft and their teams actually fly out of different sites across the western US and Hawaii as well, and make these tracks, different tracks across an atmospheric river. Here's an example of an atmospheric river that occurred in January 2018, and we had 3 different missions going out across it to make measurements. The C-130 Air Force crew also came to visit Southern California, so we were able to learn more from them and actually check out the aircraft. And recently, just in February, I was able to be part of one of the missions where I was part of an 8-hour flight out of Portland with the NOAA G4 crew. We actually released 30 dropsondes during that time period. This is a picture of a dropsonde, so these are what are actually being released, and each of these markers here is showing where one of those dropsondes was released. They're kind of similar to what we attach to the weather balloons, the radiosondes, except for dropsondes have a parachute attached to them instead of a balloon, so that it can slow them down as they approach the ocean or the ground. So this part of the mission provides invaluable measurements over the ocean. I'm talking a lot about atmospheric rivers that affect the western US. However, there are atmospheric rivers that affect other parts of the world as well. They have both benefits and hazards, because we know that atmospheric rivers, they can provide large amounts of water. This is Lake Mead, Arizona. And you can see that their reservoir is nice and full during that time period, thanks in part to some of the rain from western US atmospheric rivers. But you can also see that atmospheric rivers can lead to severe flooding conditions like here in Western Europe. And then also for the western US, the Oroville Dam spillway emergency. There was erosion that damaged the spillway, and there was an ordered evacuation of 180,000 people that lived nearby. And then we also see atmospheric rivers that can reach Western South America. And at the same time, an absence of atmospheric rivers can lead to worsened drought conditions like in southern South Africa. And in atmospheric river regions, atmospheric rivers provide up to 60% of the annual precipitation. A presence of atmospheric rivers increases the flooding likelihood by 80%, whereas an absence of atmospheric rivers increases the drought incidence by up to 90%. Atmospheric rivers will also be affected in a changing climate. The 2017 Climate Science Special Report in the 4th National Climate Assessment states that the frequency and severity of landfalling atmospheric rivers on the US West Coast will increase, and this finding is based off of an agreement amongst scientists. The report also identifies atmospheric rivers as a new 4th type of extreme storm. On that note of thinking about extremes in a current and changing climate, I'll go back to my main research questions and kind of the motivation behind my PhD work. How can research help California communities, forecasters, water managers prepare for and protect during extreme weather and water events? And broadly, what can we learn from previous extreme precipitation events to help moving forward? My specific research question is focused on how we can define, detect, and describe rapid and significant, or what I'm defining as extreme, changes in the amount of rain versus the amount of snow that's experienced during California storms. I'll start by introducing the Valentine's Day event of 2019. This was a really important event that showed up as extreme in different ways. One, it was considered an extreme multi-day precipitation event of rainfall category 1, and this is because the 3-day accumulated precipitation was greater than or equal to 200 millimeters and less than 300 millimeters, so within that range. On the bottom left here, I'm actually showing the accumulated precipitation during that 3-day time period from February 13th to 15th. According to the accumulated 3-day precipitation color bar here, there were quite a few different regions in the 200 plus millimeter range. This event was also considered an extreme because there was an extreme or exceptional AR associated with it, which was an AR of category 5. This type of extreme atmospheric river, or AR, occurs approximately once per 4 years in Northern California. Rather than it being primarily beneficial like an atmospheric river category 1, 2, or 3, it's actually primarily hazardous because it's a lot of moisture, rain, and snow at once. Here's a water vapor image for February 14th showing high water vapor content reaching the western US. And I should also mention that this Valentine's Day event, I was part of a study, Hatchett et al. 2020, that was recently published where we talked more about this event. And it was an interesting process for me to learn more about why this event was as extreme as it became. There were widespread impacts, including floods, flash floods, mudslides, and debris flows. In Southern California, Riverside County, there was 1 fatality, 30 water rescues, and $100 million in damage, and this was just for Riverside County alone. In Ramona, within San Diego County, there were floods, flash floods, debris flows, and these types of floods and debris flows were also seen in other cities and counties as well. In Northern California, at Mount Shasta, it was the largest avalanche since before 1996, and so this was a large amount of snow, and there was snow instability, which led to this movement of snow on top, causing an avalanche. During the Valentine's Day event, ground radars were also making measurements from different sites across California. And so 2 of those sites are Colfax and New Exchequer Dam. And these are 2 of the 10 radars that I'm considering in research. On the top plot, I'm showing the Colfax time series, and on the bottom plot, it's the New Exchequer Dam time series, starting February 13th and ending February 14th, 2019. On the y-axis is the snow level in 10 to the 2 meters above sea level. Here I'm actually plotting the atmospheric snow level, which is shown as the dark gray dots. And the snow level is the altitude where snow melts to rain as it falls through the atmosphere. It's an important variable to consider when we think about whether precipitation will fall to the ground as snow or whether it will fall to the ground as rain. I'm indicating the beginning of this event and the end of this event for each of the radars. And then I'm also showing some of the erroneous values in the lighter gray. What's being detected as extreme snow level changes are marked areas in red and blue. Red is for the extreme positive changes in snow level, and blue for the extreme negative changes or the extreme descents in snow level. The snow level starts at around 1,300 meters above sea level at Colfax, and then jumps up within this hour band, 1,602 meters. Remains at that higher altitude, and then drops down just over 1,500 meters remains at that lower altitude again, near around 1,300 to 1,400 meters above sea level, and then jumps up just over 1,000 meters. During this time period, you can see that there's a lot of variation in the snow level, and these sudden changes are occurring within only 1 hour, and they're very significant. For New Exchequer Dam, it's a similar story in the beginning of the event, at least, where you get this sudden jump up of 1,537 meters. Essentially, everything above the atmospheric snow level is falling as snow, whereas everything below falls as rain. This means that depending on the ground elevation, if the snow level rises suddenly, for example, within only 1 hour, as seen at Colfax around 10 UTC or 2 a.m. local time, the region might experience large amounts of rain instead of snow. Rain and snow have different impacts than one another, so this is important to consider. Rain can contribute to streams and reservoirs much more quickly than snow. Rain can also lead to flooding, flash flooding, mudslides, and debris flows, and call for an emergency response. On the other hand, snow, besides if it contributes to a chance of road closures and possibly avalanches in specific locations, accumulates and melts more gradually during warm spikes or during the springtime. Hydrometeorological instruments across California have detected various extreme precipitation events, and some of these, including the Valentine's Day event and the Oroville spillway emergency that I mentioned previously, have 3 commonalities. 1, they're associated with an atmospheric river or a series of atmospheric rivers. 2, their resulting hazards are widespread across California, but they also contribute to water supply in helpful ways through rainfall and through snowpack. And 3, and this is what I'm really interested in for my research, is they're associated with extreme changes in the amount of rain versus the amount of snow experienced. And these extreme changes can be detected using ground radars. Now I'll share more about the atmospheric snow level, or the altitude where snow melts to rain as it falls through the atmosphere. The snow level is shown here by the dotted gray line on the schematic provided by the Center for Western Weather and Water Extremes. It falls slightly below the freezing level, or the 0 degrees Celsius altitude. The snow level can be detected by radars from the ground, which are vertically pointing, and see the snow level as a level of maximum reflectivity, which is why it's sometimes also called the bright band height. The radars that I'm considering can detect the snow level up to every 10 minutes during precipitating storms. As these storms move inland, the moisture is forced upwards along the slopes of mountains such as the Sierra Nevada, where clouds can form and create these orographic precipitation enhancement events. For the western US, the cool season snow level values range between 1,000 and 3,500 meters above sea level. My goal in my PhD work is to define, detect, and describe extreme hourly changes in the snow level. The snow level is key for determining rain versus snow and impacts that are experienced in different basins and communities. If the snow level increases suddenly, that means the atmosphere has been warmed to a deeper altitude, which means that it's more likely to see rain instead of snow, depending on the ground elevation. Whereas if the snow level drops suddenly and significantly, that may mean more snow for the region. This is why the snow level is particularly important in mountain regions with complex topography. Intrastorm changes or hourly changes during storms have not been studied, but there are forecasting complexities which have been studied that are associated with high snow levels or high freezing levels or sudden changes in the snow level. And that's really where my motivation stems from. So again, for my PhD, I'm focusing on these intrastorm or hourly changes in snow level. The radars that I'm considering are provided by NOAA and the California Department of Water Resources. I'm showing the 10 different radars that I'm considering, which are all vertically pointing radars that can detect the snow level up to every 10 minutes. And I'm considering 6 cool seasons, 2015 to 2020. You can see that they're kind of spread out across the state, some in the northern region, some in the southern, a couple that are closer to the coast, and then a few that are along the foothills of the Sierra Nevada. And I'm also outlining in blue some of these high impact water basins to show that some of these regions are really key for us to focus on when it comes to precipitation events. In order to describe and investigate extreme snow level changes, we first needed to define extreme in this case. To do so, I first computed 1 hour snow level changes at all radars and all 6 cool seasons. I then looked at the percentile values resulting for the positive changes and the negative changes separately. On the x-axes here are the percentiles, and on all of the y-axes are the snow level change magnitudes in meters. In red, I'm showing the percentile values resulting for positive snow level changes for key radars, or the 5 radars which are within high impact basins: Shasta Dam, Oroville, Colfax, New Exchequer Dam, and Pine Flat Dam. For blue, I'm showing the same except for negative snow level changes for key radars. 90th percentile values for these key radars are what end up being closest to the threshold for extreme snow level changes, which is defined as 400 meters over 1 hour. In the middle, I'm showing percentile values resulting for each radar for positive snow level changes or snow level rises alone, and then on the right, the same, but for negative snow level changes or snow level descents by radar. You can see there's a spread in the resulting 98th percentile values depending on the radar, and many of them do fall below the 400 meter threshold, but the idea is to consider only the most extreme events to eliminate false positives and to really hone in on the most high impact events. As a result of this work, we've defined extreme snow level changes to be 1 hour snow level changes that are of a magnitude equal to or exceeding 400 meters. Through this work, we've also created a detection algorithm to identify where extreme 1 hour snow level changes have occurred. This algorithm uses data from radars across California, the 10 radars, and I'm again showing the Valentine's Day event here, plotted as a time series with snow level in 10 to the 2 meters above sea level on the y-axis, showing Colfax on the top and New Exchequer Dam, which is slightly to the south and east. These subplots are demonstrating exactly what the algorithm was designed to do. First, being able to identify semi-continuous snow level events. I'm showing where the algorithm is detecting the beginning of the event and the end of the event. And then within those semi-continuous snow level events, computing 1 hour changes in the snow level and identifying which of those 1 hour changes are considered rapid and significant or extreme, which is again exceeding or equaling a magnitude of 400 meters. Positive extremes, or extreme rises in snow level, are shown in red over a 1 hour time period, whereas negative extremes or extreme descents are shown in blue. Before this algorithm could be run, the first step was to apply quality check methods on the data set. The erroneous values are shown in the gray dots here. After removing those in order to remain conservative in methods to eliminate false positive extremes, we were able to run the algorithm and detect extreme changes in snow level. The Valentine's Day event and the Oroville Spillway emergency case were just 2 examples of events that contained extreme snow level changes. In total, across all 10 radars, over all 6 cool seasons, 141 extreme rises in snow level and 114 extreme snow level descents were detected. Now, some of these extreme changes occurred within the same event, but across different radars. We also found that extreme snow level changes vary by year, by radar, and by month. On the left-hand y-axis is the total count for extreme snow level changes. On the right-hand y-axis is the extreme snow level change value in 10 to the 2 meters. For all 3 right plots, or the plots in blue, we're considering extreme negative snow level changes or extreme descents. The left three plots are showing values resulting for extreme positive snow level changes or extreme rises in snow level. I'm also showing the maximum extreme snow level change values in the square line plots and the 50th percentile or median of the extremes in the circle line plots. What I'd like to draw your attention to are the colored bar plots corresponding to the left y-axis, or the total count of extreme snow level changes. We see increased numbers of extreme positive snow level changes for wetter cool seasons for 2017 and 2019. We see the same for extreme negative snow level changes, increased counts for wetter cool seasons 2016, 2017, 2019. There's also a latitudinal dependence when it comes to extreme snow level change counts. I'm plotting radars from northernmost to southernmost, with the two nearest coast sites toward the right. A significantly higher number of extreme positive snow level changes result at the northernmost sites compared to the southernmost sites and the two nearer coast sites. The same is true for extreme negative changes in snow level, except for the value difference is much more pronounced when you consider Happy Camp, the northernmost site, compared to all others. When considering the number of extreme snow level changes for both positive and negative changes, there's also seasonality. A significantly larger number of events occur between December and February. And that's true for both positive extremes and for negative extremes. These months are also peak months for atmospheric rivers. Early on in the cool season in October and November, and later on in the cool season in April, the counts are reduced. And this is also true for positive extremes. To summarize a few of the key results coming from recent work, extreme snow level changes are defined as equaling or exceeding 400 meters in magnitude within 1 hour. We found that extreme snow level changes are most common between December and February at northern sites compared to southern sites and compared to near coast sites. We've also found that extreme snow level changes are associated with higher levels of atmospheric moisture when compared to non-extreme change time periods. So this means that as these extreme changes are occurring, there's higher levels of atmospheric moisture. And to go along with that, 60% or more of these extreme snow level changes occur within plus or minus 6 hours of a detected atmospheric river, which is defined as a period of enhanced atmospheric water vapor. Next, I will investigate hydrologic and societal impacts resulting from extreme snow level changes across California, both extreme rises and extreme descents. I will also investigate mechanisms that may be driving extreme changes, including larger scale atmospheric dynamics and smaller scale thermodynamics involving temperature changes that may affect the height of the snow level. Now I'd like to switch things up a little bit. Although before I was talking about extremes when it comes to precipitation, now I'd like to talk about some of the extremes when it comes to life. I'm multiracial and grew up between two worlds in both the north-central United States in Minnesota and in the desert southwest of Arizona. My intention is not to compare my story or extremes to anyone else's, but to share a peek or a small glimpse into one life story. Growing up between worlds has its difficulties at times, but it has also offered me a unique perspective and set of experiences in this world. My why has driven me to do so much more than I would have ever imagined. I come from a low socioeconomic status background, and my single mother, she would drive us, my brother and I, to schools outside of our city so that we could get a better education. And I am fully aware that not everyone has this opportunity, and that's something that I'm always grateful for. My grandmother, my aunt and uncle, and their children have played a big role in my life as well. I'm incredibly thankful for them. There have been peaks, valleys, steady streams, storms, and moments of sunshine. I fought time and time again, even when I wasn't sure I could see a way out. Life may be chaotic and come with extremes at times, but with everything I do and each place I go, I want to remember where I come from and pay it forward to the young learners fighting battles that are both similar to and different from the ones I've faced. I'll say that this by no means represents the entirety, complexities, or depth of my journey so far, but I would like to share a few key points. So, early on, growing up in Minnesota, I didn't know much about STEM and I didn't realize that meteorology was a science yet. But I did know that I loved to see the woman on TV presenting the weather, and I thought that was pretty special. I also knew I loved nature, and part of that was because of my quirky family members who would take my brother and I on nature walks and teach us about their gardens. At the same time, there was a lot of chaos and a lot of difficulties that my brother and I faced. I would run outside in the rain during storms, and I would lay out in the grass, look up, and think about which shapes the clouds made. That was a way for me to gain peace. And so was school. I felt like it was a safe place. I loved my teachers, and I felt like they loved me too. When I was around 8, my brother, mother, and I moved to Arizona, where we faced a different set of complexities and an entirely new journey. I found support, friendships that have been long lasting. We were also living in a totally different climate now in the desert versus these harsh winters of Minnesota and the humid summers. In high school, we moved back to Minnesota, and my brother and I lived with our aunt and uncle who had two toddlers at the time, which was a new, kind of extremely different situation for us. These children now have become such a big motivation for me. They also added a third child while we were living there, and that was such a joy to see and experience. During this time period, I was also fighting extreme health battles each day just to be alive. In my final years of high school, I wasn't sure if I would be granted a life long enough to attend college. I fought each day to simply attend school, but I ultimately had no choice but to complete my final semester of high school from home, have frequent visits with physicians, and receive long and depleting treatments. At that time, my cuddly and ever mischievous toddler cousins provided a light that helped give me strength when I was at my absolute weakest. My health-related and additional battles have shaped me. They have taught me that tomorrow is never promised, and that life as we know it can be dramatically altered in an instant. This is why, after recovering, I sought an enormous amount of opportunities. I decided to attend a nearby school, St. Cloud State University in St. Cloud, Minnesota, to complete a degree in meteorology. I was intimidated by the coursework, and I didn't really know what it was all going to entail. But my advisor, Tony Hansen, encouraged me to stick it through, and it was still challenging, but I found support and I stayed persistent so that I was able to progress through my coursework. I added hydrology as a major, and then I also had mass communications as a minor since it was a special interest of mine. I ended up gaining a lot of support there through the Multicultural Student Services and the Atmospheric and Hydrologic Sciences Department. This ended up being one of the best decisions that I've ever made. They ended up providing me lasting support that I'm grateful for. I also gained a lot of opportunities outside of the university, and some of them are part of the university or part of university programs. I had my first study abroad experience through a 2-week program in South Africa. While there, we learned about different educational and social structures and visited various schools to converse with students. At one of the schools we visited, many of the students' families couldn't provide food for the children each day, so their only meal was the one provided at school. But the school didn't always have enough food for all of the students. I hold these experiences with tremendously resilient young students close to my heart. In 2012, I was selected to participate in a National Science Foundation research experience for undergraduates in the Bahamas. I was able to core sediment from lakes there and study anthropogenic climate change. This was a really exciting opportunity for me, and I was able to be a true explorer. This was also one of my very first real research experiences. I had some really exciting opportunities in the mountains of Colorado and Wyoming. There, I learned more about land management and environmental justice. During the summer of 2013, I interned at CNN in Atlanta within domestic and international weather. I was in awe at landing this position and figured out a plan to uproot to a new place, Georgia, for the entire summer. This was a chance for me to explore my first passion within meteorology, broadcast meteorology, which is what led me into the field. I recorded reels there to possibly send to television stations post graduation. I created weather graphics, which were shown on TVs across the world. I was eager and excited and loved learning from the weather team there. I had the exciting opportunity to travel to New Zealand to do fieldwork there for my senior research. While there, I was part of a larger field campaign that was multinational. We were focused on atmospheric gravity waves near the mountains. I released weather balloons all through the night and day during storm events, and also had the chance to explore. That was, again, an incredible experience. I couldn't believe that I was there. Right after completing my undergraduate, I took an internship at NASA Goddard in Maryland. This internship was in science journalism and multimedia, which are other passions of mine. I told the stories of other researchers and published my work in Goddard View magazine and on the NASA website. Right before starting grad school, I was part of a field campaign with the Center for Severe Weather Research, where we studied nocturnal summertime thunderstorms in the Central Plains. Ahead of storms, we laid out instruments to measure atmospheric variables as the storms passed over. And these were all absolutely highlights in my story. I was also still fighting for my health. I was working multiple jobs to support myself and my education. The education and experiences we gain can become powerful tools, but I've learned that wellness must be the top priority, as it is at the core of everything else. I'm incredibly grateful to be alive today, to have the opportunity to breathe in and out, to share and grow with others on this unique journey. Many of my undergraduate experiences and mentors led me to pursue a PhD, even though I didn't know what that was earlier on in my undergrad. I applied to Scripps Institution of Oceanography all the way over in San Diego, California, which was my dream school. I cried tears of joy with my grandmother when we found out I was accepted into the program. Maybe this is what all the extremes have been preparing me for. Once at Scripps, I learned students were attending the United Nations Framework Convention on Climate Change Conference of the Parties, or COP for short. This is where, in 2016, the Paris Agreement was adopted. Nearly 200 countries committed to climate change mitigation and adaptation. For a long time, at least since high school, I'd wanted to be involved with the United Nations, something global scale, to learn and share about the environment and the world around us. As a student, I'd wanted to be part of the COP, but knew, like everything else, I'd need to earn it. When I inquired in my second year of grad school, I was waitlisted for the next year, because it made sense for the others to have opportunities before they graduated, of course. To prove my interest, I volunteered to write about Scripps researchers' science for the Scripps website. The next year, I had the opportunity to attend my first COP, COP23 in Bonn, Germany in 2017. It was an eye-opening, incredible, enormous experience. I presented my first press conference there on atmospheric rivers, which, to my knowledge, is the first time atmospheric rivers has been one of the key foci of a presentation there. I still find it awe-inspiring to think that I, a once timid, curly girl who was born into some type of chaos, would be the one to share about atmospheric rivers. I went on the next year to present at and learn from COP24 in freezing cold Katowice, Poland. There, I was further introduced to the idea of community resilience and ecosystem-based solutions, which I found fascinating. For this year and the following year, it was important to me to find a way to make it to the COP that didn't require taking up a Scripps spot, which are limited but in high demand. What I mean is that each NGO or non-governmental organization representing each institution only receives a set number of participant badges, and the interest at Scripps in particular typically far exceeds that limit. Since I attended the first year in Germany with a Scripps badge and found the experience to be life-altering, it was extremely important to me for others to experience that opportunity. So for the next 2 years at COP24 in Poland and COP25 in Madrid, Spain, I sought different paths to attend that would free up at least one badge for new Scripps participants. Thanks to Diane White Husick, I attended as a dual Moravian College/Scripps delegate instead. I'm hugely grateful for Diane and Gillian Bowser of Colorado State University, who have become two of my cherished mentors. I'm also grateful to Rob Monroe and Brittany Hook for leading our Scripps group and making this possible. Most recently, I participated in COP25 in Madrid, Spain. It was originally scheduled to be held in Santiago, Chile, but social injustices, which led to an uprising, resulted in a switch over to Madrid less than a month before the conference. Being that it was my third COP, I worked with Gillian Bowser at Colorado State University and her multinational, multi-institutional, multidisciplinary crew to prepare. This time I took on a peer mentor role to help prepare students who'd be attending the COP for their first time. This was a new, challenging, and fulfilling role for me to take on. We created presentations focused on the UN Sustainable Development Goals to share at the COP. Our group focused on ways in which our universities have and can contribute to climate change solutions through composting and sustainability efforts that help strengthen soil, reduce waste, and reduce food insecurity. At this COP, I also sat in on more formal negotiations and began to seek opportunities to speak with negotiators and delegates and share science in new ways. This was a group of us from Scripps speaking with Representative Scott Peters. This is a comment from a friend from high school that I wanted to share. This particular friend knew me during some of the most challenging times where I felt like everything was breaking into pieces, and I really wasn't sure how to put them back together. This comment stands out to me because it reminded me of the quiet, timid little girl who had big and bold, colorful dreams. I now see myself using my voice with others in potentially powerful ways that I never imagined. With the spirit of the United Nations framework in mind, I typically also try to share a call to action with colleagues and others. We should care about humans whether or not they do science, but we also know that humans are the ones that do science. We should care about brutalities and injustices towards humans. We've also seen studies that show that as teams we can go further with heterogeneity or diversity. We can come up with more innovative, equitable, sustainable, creative solutions long term, and that includes solutions to complex climate change problems. And as a bonus, studies have shown that mutual vulnerability strengthens teams by creating a sense of trust. I call on colleagues and others within the community to track ways their institution, team, neighborhood is or is not upholding JEDI goals. Who is and who is not represented or heard at the table? What actions can you take or can your group take to help dismantle problematic structures, to unlearn and relearn? And to ask, this is also something I ask myself, how can I be a better ally or advocate? This photo is from a recent Rocky Mountain Science and Sustainability Network summer school in 2019. I originally attended as an undergraduate student in 2014, and it was one of my first times exploring the mountains. In 2019, I was able to go back as a mentor, and it was a very fulfilling experience. We had students with various interests, and we all were able to enjoy nature together, and we continue learning from one another and practicing ways to be stewards of the environment. I'd like to express gratitude for my loved ones, mentors, and teammates. I'd like to thank my co-authors, Joel, Anna, Ben, Marty, and Brian, and also mentors, Art, Amin, Diane, Gillian, and many others. I'd like to thank centers that have shown me support through my work, CW3E and NOAA centers. I'd also like to thank individuals and organizations who have shown me support in various ways through funding opportunities and opportunities to participate in the United Nations setting. The photo I'm showing here is Lake Oroville near one of the radars that I study. and I had the opportunity to go visit thanks to CW3E. I owe my utmost honor, respect, and gratitude to forebearers before me, whose lives and freedoms were stolen and who fought, suffered, and sacrificed to make this world a better place. I respectfully acknowledge the ancestral unceded land of the Kumeyaay, which UC San Diego occupies, and the ancestral territory of numerous Native nations on which atmospheric and environmental research is conducted. I'd like to leave you with one more message. Tomorrow's never promised, but what we choose to do today can make a difference in our lives and others' lives, in our neighborhoods, our institutions, and communities. Somehow, through storms and uncertainties, through extreme pain, relearning, rain, and thunder, we're still rising each day like the sun and greeted each evening by the moon. With introspection and growth through our storms, compassion, persistence, and the gift of today, we can leave this world better off than it was before we entered into it. Thank you for your time today.